So the title of my thesis is Fundamentals of Interactions Between Cellulose Materials and its Implications on Properties of Fibrous Networks. I'm going to start with an introduction, some background information, and then go into the results of my work. So climate change is one of the most pressing issues of our time. The Earth's climate is rapidly changing, mainly due to human activity, primarily the release of greenhouse gases into the atmosphere. And we are already witnessing the undeniable consequences of climate change, from extreme weather conditions to the rise in sea levels, and this threatens both ecosystems as well as human civilization. The pulp and paper industry is a major source of waste generation, responsible for about 4% of the world's energy use, and about 100 million tons of CO2 emissions per year. However, with these challenges, we have an opportunity to transform the sector by implementing new methods to prioritize environmental sustainability. In Sweden, the pulp and paper industry is plays a very important role for the national economy, since 70% of Swedish land is covered by forests. And in order to meet the increasing demand for sustainable resources, resource conservation is crucial. And Sweden has one of the highest rates for paper recycling rates, with over 80% of paper consumed being recycled. And this reduces the need for new materials and also alleviates pressure on natural ecosystems. Fiber-based materials are increasingly in demand nowadays, primarily due to their renewable and sustainable characteristics. And cellulose in particular, being the most abundant polymer on Earth, holds immense potential for sustainable applications. And in order to harness the full potential of cellulose as a material, we need to understand how the mechanisms governing cellulose interactions at the molecular level, which brings me to the thesis objectives. This work aims to study the molecular interactions in cellulose-based materials by developing methodologies for investigating and quantifying interactions at cellulose-rich interfaces, by studying the effect of additives on cellulose surface interactions and network formation, and by using the acquired knowledge to improve material performance. This work aligns with several sustainable development goals, and particularly the ones highlighted here. So, wood has a natural hierarchical structure, ranging from the wood stem all the way to the individual fibers. And the fiber wall is composed of fibrils covered with hemicellulose in a matrix of lignin. And the fibrils themselves are composed of linear cellulose chains. Wood fibers are already being used in many applications, essentially in material science, due to their excellent mechanical properties. And to be able to expand these applications, we need to understand how fibers interact with each other, essentially how a fibre-fibre joint is formed. And the formation of a joint is the joining of fibers to form a cohesive structure. And this requires overcoming energy barriers and establishing close contact to allow for the development of a molecular contact zone. And this, where we can have direct contact or at a distance where van der Waals interactions can occur. This molecular contact zone is a result of molecular adhesion, which are the attractive forces that occur on the molecular level when bodies make contact. And molecular adhesion is very important for the formation and consolidation of fiber networks, and ultimately for the performance of paper products. The inherent properties of the fiber surface and its heterogeneity makes it very difficult to study their interactions. And so in this case, model materials present a great alternative where they provide a simple and controlled environment, and they can be used to elucidate the complex mechanisms at the molecular level. And in this work, regenerated cellulose beads have been developed and used as model materials to study cellulose interactions. So I've divided the results into 4 parts. Part 1 focuses on model systems for studying cellulose-cellulose interactions. Part 2 is on quantifying cellulose interactions. Part 3 focuses on studying the effect of additives on cellulose interactions. And part 4 focuses on fibrous networks, where we study the effect of density and additives on mechanical properties, on paper mechanical properties. So let's start with part 1. The regenerated cellulose beads are prepared by dissolving pulp fibers into DMAC and lithium chloride, and then precipitating the dissolved solution into a non-solvent. And in our case, we are using ethanol, creating these gel beads, which are then washed thoroughly with water to remove any presence of the solvent. And these cellulose beads have a diameter of around 1.5 millimeters in wet state. When they dry, they shrink to around 35% of their original size. And when re-swollen in water, they swell back to about 55 to 60% of their original size, depending on the charge density of the cellulose. They have a nanometer smooth surface measured with AFM, which makes them excellent for adhesion studies. In paper 1, grazing incidence small angle X-ray scattering technique was used to study the development of the cellulose interface during drying. And this was, for this, a cellulose filament and a cellulose thin film were prepared and used as model materials. The filament was used in this case to create a larger contact area with the film and was prepared in a similar way as the beads. However, instead of dropwise precipitation, we used a continuous flow to create the filaments. And the GSAX measurement was performed by placing the wet filament on the cellulose thin film spin-coated on silicon wafer and allowing them to dry while exposing the interfacial area to a micrometer-sized beam. 2D patterns were obtained and analyzed by performing horizontal and vertical integrations on the Yoneda peak, which is the area where we have the strongest scattering. And the dimensions of the filaments were monitored using an optical microscope. So these are the curve on the left is the intensity curves obtained from the horizontal integrations of the 2D patterns at different evaporation time. And from these curves, we're able to extract a characteristic length scale, which is plotted against the evaporation time in the next figure. And this gives us an idea about the average distance between cellulose aggregate structures, which varies significantly during drying. And this means that we have structural changes in the filament during drying. When looking at the intensity curves obtained from the vertical integrations of the 2D patterns, we can see that we have 3 different peaks. Peak 1 is obtained when the wet filament is placed on the cellulose film, and therefore is attributed to the newly formed interface between the 2 materials. And peak 2 is attributed to the surface or the cellulose thin film. And when we increase the evaporation time, we can see that the peaks broaden and shift to the right, which means that we have increased roughness and continuous diffusion of cellulose chains in the interface. And when the 2 surfaces are completely dried, we can see that the purple curves completely broaden and shift to a higher QZ. And this means that we have a newly formed, rougher and more dense interface, which is a result of structural rearrangement at the interfacial layer. Adhesion is present at different length scales, from housing construction, wound dressing, dental filling, and all the way to muscles adhering to rocks underwater. And by studying adhesion, we can either quantify or measure the energy needed to separate materials, or we can use it to understand mechanisms behind the adhesion. And our aim in this work is to understand the mechanism behind the making and the breaking of a fiber joint. And so for this, and to study the adhesion between 2 cellulose materials, we performed pull-off measurements of the cellulose beads dried on a cellulose thin film. And this was performed by placing the swollen cellulose bead on the silicon wafer, on the cellulose film spin coated on silicon wafer, allowing them to dry, and then pulling off the bead and analyzing the surface of the bead as well as the surface of the film after separation. So when looking at the SEM and the AFM images of the cellulose film, we can see that there's material missing in the form of a ring, which is perceived to be found on the surface of the bead after separation of the film from the film. And when looking at the AFM images of the cellulose bead, we can see that there's a homogeneously distributed fibrous structure from the film and the dry bead at the interface. And this supports the suggestion that there's a diffusion of the external layer of cellulose chains into the cellulose film. So as a summary for part one, high-resolution techniques were used to provide great insights into the interaction between cellulose surfaces and the strong adhesion between two non-crystalline cellulose surfaces are mainly due to the molecular interdiffusion and structural rearrangements of cellulose at the interface. Now on to part two. Contact adhesion measurements were performed using a custom-built contact adhesion tester, and this is performed by using a cellulose bead and a cellulose thin film as model materials. This measurement is performed by placing a dry cellulose bead on a force sensor and gluing a cellulose film on a glass slide, which is connected to a translation stage. And the two materials are brought into contact by moving the translation stage downwards until reaching a set load or a trigger value. And then the two surfaces are separated by retracting the translation stage upwards until separation of the two materials. Typical curves can look like this, where we can, loading and unloading curves. We can see that we can either load the two materials until reaching a trigger value and then directly separate them, or we can keep them in contact for a certain time before unloading the two materials. And in this project, we tested 3 different cases. Case 1 is a cellulose bead against a PDMS surface. Case 2 is a cellulose bead measured against a cellulose film spin-coated on PDMS. And case 3 is a cellulose bead measured against a cellulose film spin-coated on a glass slide. And the morphology on the surface of the beads, as well as the films, were analyzed using SEM and AFM. And we can see that the surface roughness is slightly higher on the cellulose beads, and we have an open network of the cellulose films, which is not affected by the underlying substrate. So, starting with case 1, where we have a cellulose bead measured against a PDMS film, we can see from the loading and unloading curves here that there's attraction on approach and on separation, where the surfaces jump into contact, and then when separated, we have a pull-off force. This pull-off force is connected to the contact area, which can be monitored using an optical microscope throughout the whole measurement. And when we increase the trigger load, we can see that the pull-off force remains almost constant. And this means that it's independent from the applied load in this case. Looking at case 2, where we have a cellulose bead measured against a cellulose film spin-coated on PDMS. We can see that there's no attraction on approach. However, we have a separation force. And this separation force increases when we increase the load from 25 millinewtons to 100 millinewtons. And this increase is related to the increase in contact area, which we can see in the optical images. Due to the slightly high surface roughness of the cellulose beads and the open network of the cellulose films, it is suggested that molecular interlocking is formed when the surfaces are kept into contact. And this is supported by the image of the contact area here, where we can see white patches, which indicate that there was material transfer upon separation. And the presence of PDMS, or a soft backing substrate of the cellulose, promotes the deformation of the surfaces, and therefore the formation of a larger contact area and ultimately larger interlocking between the surfaces. Now looking at case 3, where we have a cellulose bead, again measured against a cellulose film spin coated on a glass slide, we can see that there's no attraction or separation. However, there's a different behavior where we see an increase in the force where we start to unload the two surfaces. And this force increases when we increase the contact time between the surfaces between unloading. We also have a separation force when we increase the contact time. The separation force happens gradually, and when we analyze the surfaces after separation on the film as well as the cellulose bead, we can see on SEM that the morphology of the surface is different, and we have several breakage areas centrally located on the surface of the film. And this suggests that there were nanoscale antidigitation of the surfaces. So as a summary for part 2, the interactions between dry cellulose materials were investigated using a custom-built contact adhesion tester. Depending on the configuration of the contacting substrate, the interaction shows distinct behaviors, where in the case of the presence of a soft substrate, a molecular interlocking is promoted due to the surface roughness and deformability. And in the case of presence of a hard substrate, a closer contact was established, and the surfaces and nanoscale interdigitation occurred when increasing the contact time between the two materials. Now we move on to part 3, where we study the effect of additives on cellulose interactions. In order to examine how additives will affect cellulose materials and how surfaces will come in to join together, we used layer-by-layer technique to adsorb oppositely charged polyelectrolytes on the surface of the gel beads. For this, we used polyamine hydrochloride and hyaluronic acid as the polyelectrolytes, since they have been used and showed very good adhesive properties previously. And the first step is to figure out how much polymer is adsorbed on the surface of the material. And for this, we performed a scratch test using AFM to measure the thickness of the LBL film. And we used stagnation point adsorption reflectometry to measure the adsorbed amount of the polyelectrolytes on the surface. And we can see that by adsorbing more layers on the surface, the adsorbed amount increases, as well as the film thickness. Now, to study the effect of these adsorbed layers on the surface on the elastic properties of the gel beads, we performed a compression test of the gel bead using a modified version of the contact adhesion tester, where we compressed the beads to 20 to 30%, and the modulus is measured in the first 10% region. We can see that the elastic properties are not significantly affected by the adsorption of the LBLs on the surface. However, we can see that the highest charged beads are the most deformable. And these adsorbed layers on the surface are expected to alter the structure of the surface of the beads. And this was analyzed by doing SEM, AFM of the surface of the dry beads before and after adsorption of 5 and 10 bilayers of PAH and HA. And we can see that there are structures formed on the surface, and the surface roughness increases significantly from about 5 nanometers up to 183 nanometers when adsorbing 10 bilayers. And these structures forms on the surface will affect how these surfaces will come together and dry. And to create, to be able to study this, we created a model joint using the cellulose beads by drying two cellulose beads together. And one of the advantages of using the beads as a model material is their spherical shape, which allows us to visualize the contact area before separation. And this is done using SEM, where we can see that the AFM images are further supported, where we see the increased roughness of the LBL treated materials compared to the unmodified ones. And when we look more into in details, we can see that the surfaces are very affected by the LBLs, and the joining is also very different in the LBL treated materials. And what's happening here is basically we have, after adsorbing 5 bilayers of PAH and HA on the surface, we have an LBL film of around 70 nanometer thick. And when this LBL film dries, it will shrink and wrinkle, and therefore will alter the underlying cellulose bead. This means that the cellulose bead will have built-in stresses from the inhomogeneous drying of the two materials. And the drying of the LBL treated materials will also cause shrinkage of the contact area, which is much rougher than the untreated materials. Now, to examine the adhesive properties of these model cellulose joints, we performed pull-off measurements using our contact adhesion tester by pulling off the beads in the joint in the Z direction. And the stress at break was obtained by normalizing the pull-off force with the contact area, which was measured after separation of the two materials. And here we can see the strength of the model joints, which both medium charge and high charged beads show similar joint strength. And we can see that the contact area decreases when adding the LBLs on the surface, and and the highest charged cellulose beads have a larger contact area since they are softer and able to deform more. To further investigate the effect of the LBLs on the surface, we dried the cellulose beads on carbon tape. So previously, when the beads are dried, they are free to move when they shrink, and therefore are able to form a more closely packed contact area. However, when they are dried on carbon tape, they are restricted from moving, and therefore when they shrink, this causes necking and stretching of the polymers at the interface. And this means that the long-range interactions are due to the stretching of the polymer complexes, which are formed at the interface in the LBL film. So as a summary for part 3, regenerated cellulose beads can be used as excellent model materials to investigate the mechanisms by which cellulose-rich surfaces form initial contact and finally dry together to a joint. And microscopy and adhesion measurements show the fascinating effect that strength additives have on cellulose joints. And the added LBLs influence the properties of the cellulose bead as well as the formation of the contact zone between the surfaces during drying. Now on to part 4, where we focus more on fibrous networks. So first in this work, we prepared CNF filaments by coaxial spinning of a CNF solution into hydrochloric acid solution. And this technique was previously developed and was used to create our CNF filaments, which are then used to create a model joint by hot pressing 2 filaments together in a cross shape and mimicking a real fibre-fibre joint. The tensile strength of the filament joint was tested by doing tensile testing in the shear direction. And the filaments were then LBL treated with PAH and HA. And the joint strength is presented in the box plot here. And we can see that the average strength of the joint remains almost constant when we increase the added bilayers on the surface. However, the lower bound here increases, which suggests that the weak joints are eliminated by adsorbing more polyelectrolytes on the surface. Surface treatment was also performed on bleached and unbleached pole fibers using PAH and HA, and the adsorbed amount on the fibers was measured using nitrogen analysis, where we can see that we have linear adsorption of the polylectrolytes on the surface of the fibers. And then the mechanical properties of the paper sheets formed with the LBL treated fibers were tested using tensile test, and we can see the increase of paper properties or paper strength with the adsorbed bilayers on the surface of the fibers. The Z strength of the paper is mainly affected by the strength of the fiber joints, as opposed to the shear strength with the tensile strength of the paper, which is more affected by the strength of the shear fiber wall. And therefore, by testing or evaluating the Z tensile properties of the paper, we can evaluate the effects of the treatment on the fiber-fiber joints. And we can see by doing Z tensile tests on the LBL treated papers, we see also an increase in the strength of the paper, both for the bleached and unbleached materials. To further investigate the effect of the treatment on the strength of the individual fibers, we developed a new method to to measure the Z strength of the fiber joints using the CNF filaments. And we compared it with the data from the joints of the cellulose beads, since they're also pulled off in the Z direction. And we see that we have a similar trend where we have an increase of in the joint strength after LBL treatments. The filament joints were imaged with the SEM before and after separation, and we can see that the LBL treated joints resulted in cohesive failure. Next, we wanted to study the combined effect of increased density as well as the LBL treatment. And for this, we performed different techniques to obtain 3 different ranges of density levels. And this density of the LBL treated papers is slightly affected by the adsorbed layers. However, the effect is not clear or significant. Next, we studied the mechanical properties of these LBL treated papers, and we can see from the specific stiffness and strength properties of the papers that the properties increase with increased density for both materials. And also, the properties increase with the added bilayers, which is also seen at high densities. To evaluate the failure mechanism of the paper sheets, the samples were imaged with the SEM after the tensile measurements. And looking at the SEM of the papers at low density, we see that we have a lot of fibrillation and fiber pullout for both the untreated and the treated papers. At high density, we can see that we have much less fibrillation of the high density sheets with no bilayers. And with 5 bilayers, we can see that we have almost no fibrillation, and the crack is clean and straight in the thickness direction, which means that the fiber joints are strong enough not to be the limiting factor. In order to investigate how the effect of moisture on the properties of the paper sheets, we performed hygroexpansion expansion measurements by exposing the papers to different cycles of relative humidity. And hygrospansion measurements provide evaluation of the built-in stresses in the network. And here, the strain and the moisture content were measured simultaneously. The hygrospansion coefficient relates to the slope of the presented curves. We can see from the increased density we have a lower expansion at high moisture, which means that the stresses are built in during drying. With the added bilayers at low density, there's no significant change. But with added bilayers at high density, there's a significant change in expansion, and this means that there's additional built-in stresses. The mechanical properties of the paper were also tested post the hygrospansion or post the moisture cycling to assess how the moisture cycling affected the mechanical properties or the dried-in strains. And looking at the craft material, we can see that the effect of the surface modification vanishes for stiffness, and there's slightly reduced strength after moisture cycling. And for the bleached CTMP materials, we can see that the properties are retained despite great release of the dried-in strains. The shrinkage caused by the added LBLs, which is seen in the bead joints, might explain the increased paper stiffness. And since we have shrinkage, this means that there's built-in stresses which are released by the adsorbed moisture. And in the case of the craft materials, which have a softer fiber wall, which will induce a larger shrinkage and therefore a larger effect on the stiffness. So as a summary for part 4, a new methodology was developed to clarify the effect of surface treatment on the mechanical properties of fibrous networks. The impact of the surface modifications is clearly visible even at high density, inducing more fiber fracture. And moisture cycle does seemingly not affect the performance of CTMP materials despite great release of dried-in stresses. And the LBL effect on stiffness seemingly disappears for craft material after moisture cycling. So as a general summary, cellulose interactions were investigated at different levels using cellulose model systems. The strong adhesion between two non-crystalline cellulose surfaces is mainly due to the molecular interdiffusion and structural rearrangement of cellulose at the interface between the surfaces. LBL-modified materials were used to study the effect of additives on the formation and strength of the dry joints, showing the importance of both the making and the breaking of the joints. And finally, the effect of additives on the mechanical properties of fibrous networks was studied at different density levels. The strength of fibre-fibre joints were compared with sheet properties, and by tailoring the surface properties of the fibers, strong interactions have been achieved, leading to enhanced properties and enhanced utilization of the inherent fiber properties. And so with this, we have studied cellulose interactions at different length scales, using model systems all the way to fiber networks. So I would like to thank my supervisors, Lars Wågberg, Torbjørn Puresen, and Søren Östlund, my collaborators and co-authors, and thank you to KW and Stora Enso for funding my PhD, everyone in FPT and Fiber Technology Division, and thank you all for listening.